So welcome to the lecture. We will start with a brief recap. So remember that we have identified the Lorentz transformation as a Jacobian map when we change the coordinate system from x to some x prime. So this is the element of the Jacobian matrices, and from that it is evident that this mu denotes the row index and this alpha denotes the column index, and hence this convention, this upper index mu associated with the Lorentz transformation matrix denotes its row, and the lower index, which is written slightly far away, denotes the column. Similarly, the inverse Lorentz transformation is associated with the inverse Jacobian map, which is given here. Then we argued that the tangent space associated with each point of Minkowski spacetime can be equipped with a vector space structure, and we denote that vector space by this symbol. This is nothing but the tangent space associated with the point P in the Minkowski space, and the elements of such vector space can be written like this way, where this v mu is the component and e hat mu is the basis vector. We will choose the coordinate basis where e mu will be simply del del x mu, which is in short we have written like this, del mu, and the component of this vector transforms in this way under Lorentz transformation, and this is the defining relation of a vector. Then we can also define a linear map which takes this vector and gives us a real number, and let's call this map by omega, and set of all possible linear maps from this vector which gives you this real number constitute a vector space, and we call it a dual space. And if it is dual to this tangent space, we call it cotangent space. It is denoted by this symbol T star, the dual space associated with the tangent space at the point P in the Minkowski space. And then this map omega we call the one form, and we can again write it in terms of a component alpha and basis vector theta alpha, and we have actually identified this theta in coordinate basis with the coordinate differential, and we derive that this component of one form transforms this way. More specifically, under inverse Lorentz transformation, its component transforms as written here. Okay. And this one form is also known as covariant vector, but we will use the modern terminology of one form. Like vectors also sometimes known as contravariant vector, we will simply say or call it as a vector in all subsequent discussion. Now, given these two definitions, we can now define a general tensor of rank P and Q. So let's do that. So our tensor of rank P comma Q is nothing but a multilinear map which takes P one form. So remember, the one forms are element of this dual space which is denoted by T star, and there are P of them, and then also it takes Q number of vectors which are elements of this vector space which is denoted by T. So there are Q number of them, and then it gives a real number. Remember, this should be a multilinear map. So you can view this as like a slot machines where there are first P slot you take omega 1, omega 2 up to omega P. These are one form, so P one form. Then in the next Q slot it takes like Q different vectors which is denoted by V1, V2 up to VQ, and this gives a real number R. So we can identify a basis for this tensor which takes this form that we denote it by the symbol E hat, which will have P number of lower index which we denote by mu1, mu2, mu p, and then it has Q number of upper index which will have mu1 to mu q. Then it takes this p number of these basis vectors of one form, which we denote by theta. So there are p of them, and then it takes q number of these basis vectors of vector or contravariant vectors, which we denote by e hat, and here, and this gives the delta function. So theta alpha 1, so this alpha 1 with the mu1 index gives the delta function, alpha 2 with mu2 gives delta function, and so on. And similarly for this eta hat, so eta hat beta 1 with this upper index mu1 gives the delta function, and so on. So there are these again, from this there are q number of these delta functions comes. So these are Kronecker delta. Remember, when we call these delta functions, remember these are Kronecker delta. That means when these two indexes sum, it's 1, or if it is doesn't take the same value, it is 0. And each of these alpha, beta, each of these indices, the Latin, the Greek indices takes value 0, 1, 2, 3, as we are working in 3+1 space-time dimensions. So in coordinate basis, using the coordinate transformation law, we can identify the E as a tensor product of these dels, which is del x mu1 and so on, and there are p of them, and then there is a tensor product of this coordinate differential, there are q of them. So just what we have done when we are defining vectors and one form, you can repeat the same exercise and you can easily identify this generalized basis here in terms of the tensor product of del and the coordinate differentials. Okay. And remember, these are tensor products, so these are ordered products. So if you change the ordering, so it will give you another basis. Ordering is important in general. And given these bases, we can write down this a tensor of PQ rank in terms of a component in this particular coordinate basis, which we denoted here. So there are P of the upper indices associated with these coordinate basis dels, and there are Q of the lower indices, so that with this coordinate differential basis, which goes from mu1, mu2, mu3. Remember, each of these mu1, mu2, mu2 takes 4 values, 0, 1, 2, 3, and there are P of such index. Again, each of these mu takes 0, 1, 2, 3, and Q of such index. So it has a much larger components than a single vector or one form. So it is the element of a much larger space than the individual vector space or the dual space. Okay. And again, this is the ordered product. So in general, if you want to interchange mu and mu2, it gives you a different tensor. Okay. So now let's take some example to understand it better. The first example is 0, 0 rank tensor. What is that? It's nothing but a scalar function. It does not have any basis associated with. Okay. Then let's take an example of 1, 0 rank tensor, which we can denote in the coordinate basis as 0 as this is just the vector that we discussed earlier. A physical example of such vector will be the 4 velocity. Then what about 0, 1 tensor? In this language, G mu del x mu. Remember, here there is no P, so there is no upper indices, but there is one lower indices associated with this one of the coordinate differential basis. This is nothing but the one form. And physical example will be the electromagnetic potential. So we will see that we can collect the electric scalar potential phi and denote it by some A0 component, and there are three component of the magnetic vector potential, A1, A2, and A3. This is like this three vector, and together these four components form the one form, which we can write it as A mu dx. So this is the electric scalar potential. This is the magnetic vector potential. Again, we will come back to this when we will try to write down the Maxwell's equation in terms of these languages of tensors and so on. Okay, and then what about the 1,1 rank tensor? It denoted, so it will have one upper index, one lower index in the component del mu. Remember again that this is an ordered product, and in general del mu not equal to dx. Okay. If you change the ordering, you get a different tensor. So which means that T nu del mu is not equal to T nu okay. So remember the convention is that the index associated with the del basis is written upwards closer, and the index associated with the coordinate differential basis is written down away. And if you interchange it, that this now becomes associated with the del, but coming after dx mu, so it is far away, and this is downwards but coming closer because it is associated with the dx mu, which is coming fast now if you interchange the order. So loosely speaking, T mu nu not equal to T nu in terms of the component, unless there is some symmetries are there which only appear in special cases. One should be mindful that if you interchange this ordering, you will get in general a different tensors. So please be mindful about this fact. Now let's take an example of 2,0 rank tensor, which is basically two upper indices in the component. Okay. So a physical example will be stress energy momentum tensor. So in general, we'll see for this case also, T12 is not equal to T2, for example. Okay. Because again, you see, this mu is associated with this, mu is associated with the second one, and this ordering matters. So let's, and each of them takes three values. So let's take nu1 and nu2, and typically this is not equal to when it takes 2 and this is 1 in general. So we will discuss more about stress energy momentum sensor. It will play a huge role in context of our. And then let's take an example of 0,2 band tensor. Have two indices lower set with these two coordinate differential basis. Okay, and a good physical example of such tensor is the Maxwell field strength. Again, we will encounter this in electrodynamics. It is written as a S mu nu. So this is a special example in the sense that it is antisymmetric. If you interchange the two index, it takes a minus sign. And this is also known as something called a two form. We will discuss these things in details when we discuss differential form general slightly later on. But nonetheless, this is one physical example of a 0,2 rank tensor. And there will be more in this course as we go on. Okay, so now let's discuss one thing, something called index contraction. So let's take a simple example. Let's take one form omega acting on a vector v. Okay. So now we can write these v in terms of a component and a basis, and we will always work in coordinate basis. So remember, this map is a linear map. So this is just a number at this point. It will come out. New. Now this omega also we can write in terms of a component and a basis. Let's say omega nu dx nu. Now we have actually defined this map. We are working with such basis so that this map gives you the component of Kronecker delta. So this will give omega v. So remember that this is nothing but delta nu mu. Let's write it down, delta nu mu. And then we can simply get this. Why? Because you see that this is non-vanishing only when mu equal to nu. So then this product is non-vanishing when this nu has to become same as nu. Now we can see that this object do not possess any free index. In fact, this indices mu is repeated, which means it's summed over. And this is we call the contracted indices are contracted indices. So now let's check the Lorentz transformation property of, suppose this goes to some omega mu prime, mu prime under Lorentz transformation, then what happens? So we know that omega transforms under inverse Lorentz transformation. Following way, mu omega, and V will transform under Lorentz transformation, lambda. Now these are just some number, then we can rearrange it in the following way. Lambda remember, these are just some number, so forms a scalar product. So you can just rearrange. And we know that this, by definition of a matrix times a matrix inverse, nothing but a omega delta, then nu lambda omega, and this gives again. So we can see that under Lorentz transformation, this object means invariant. That means it forms a Lorentz scalar. Also, you can see that as all the indices are contracted, these objects is basically a 0,0 rank tensor, which is just a number or in general a function without involving any basis, and it remains invariant transformation, which is the definition of something called a Lorentz scalar. So in general, you can extend this argument for a product of arbitrary number of tensors, or rather their components. So suppose now we give you the following, that let's take 3 tensor and let's take their component, 0,2 rank tensors, the component of some 1,0 rank tensor vector, such that these new indices are contracted, and then you have a 1,2 rank tensor where these new indices are contracted, and let's say this lambda. So you can easily show that these transforms as a component of a 0,2 rank tensor. So the lesson is that whenever you are doing this contraction with multiple tensors, so the end product will transforms according to the number of the free indices. In this case, there are 2 free indices, which is downward, so it transforms as a component of a 0,2 rank tensor. So product transform under Lorentz transformation determined only by the free indices. Important. So check it explicitly. So we leave that as a homework exercise for you to check. Now we know that this in general, this tensor of rank p comma q will transform in a certain way under Lorentz transformation. Let's write it down explicitly how it transforms. So suppose you go from a x coordinate system to x prime coordinate system, the component of a p comma q and tensors, we denote by this, will go to some t prime mu q. So now this will transforms in the following way. So all the upper indices transforms under the Lorentz transformation element of this form mu1 alpha into alpha from alpha p, and this alpha 1 alpha 2 will be contracted, and all the lower indices will transform inverse Lorentz transformation of the form beta. Okay. So although in general it transforms under Lorentz transformations following this rule, there are some special tensors whose component remains invariant under Lorentz transformations, and they are called as invariant tensors. So let's try to write them down. So first one is the Kronecker delta that we are using repeatedly. So we have written down this following thing: delta mu nu, the component of this delta. Right. This is just coming from the definition of a matrix multiplying with its inverse, and then we can rewrite it as because this is only one when alpha equal to beta and alpha not equal to beta anything, so you can just rewrite it. So now compare with it with the definition of a 1,1 rank tensor if of the form, and it transforms under a Lorentz transformation this way: mu alpha so if you compare this, so you can identify that these are nothing but a component of a 1,1 rank tensors, and not only that, the components remain invariant under Lorentz transform. You can see that you get back the same component after doing a Lorentz transform. So let's formally write it down: the Kronecker delta here. Delta, the 1,1 rank tensor component we denote by delta x, and it's an invariant tensor. Invariant means that this T prime mu nu should be equal to T mu nu in the unprimed coding. Okay. The next one will be the metric tensor. Which is a 0,2 invariant tensor. Let's write it down. So first, let's again write down the squared element of the Minkowski line, which is this, and we know that this remains invariant. We change from one inertial frame to another inertial frame, and again write it. This is we have extensively discussed, and the eta mu nu is the component of the metric tensor, which is a 0,2 tensor. So note that we have denote these coordinate differentials with the upper indices. Hence, to form a scalar, this must have two indices downwards, and we know that these objects transforms as a component of a 0,2 tensor. That is what we discussed just now. So in this case, 0, 0 is minus 1 eta ij is delta ij, and all the diagonal components are either plus 1 or minus 1, and the off diagonal components are 0. And it's also symmetric. It's a special example of a 0,2 tensor because it's symmetric. So remember that although we are writing this way, this is actually should be a tensor product. It's the tensor product that we are omitting because the fact that this is like a symmetric, so can interchange mu and nu, it remains same. So this is a very special case. Otherwise, as we discussed, that you have to be careful about this order. We can define this tensor eta mu nu dx nu. And we know that Lorentz transformation preserves this metric. So this is an invariant tensor as well. But let's repeat that same exercise using this index notation. So we know that this will transform under inverse Lorentz transformation like this way. Now remember that lambda, the elements of this Lorentz transformation are denoted by this. This one is row, this one is in the column. But if you do a transpose, then you are basically interchanging the row and column. So in this notation, equal to the transpose of it, then, and you have interchanged the row and column. So this beta, the down coming to closure, the alpha, which is right. This is simply saying that when you took a transpose, you have interchanged the row and column. So keep that in mind. What we will do is that we'll replace these by of t, mu and yeah. Bring it here. So these are just a number multiplying each of them. So we can rearrange it without bothering about in order. We are using, remember the index notation, component by component. We are looking at this, and these are each for each component just number. Then rearrange always. And now in terms of matrix multiplication, it makes sense because this is row multiplying a column, then this row should multiplying a column, and then it's the row. Okay, that is the trick, that we have replaced this by the transpose where the row and column are interchanged basically. So this is now the column, this is now the row. And then we just remember rest of the indices are contracted and only these mu are free indices. And then we can use the definition of this Lorentz transformation, which simply says that this is equal to theta. And hence the proof that this is a invariant 0,2 tensor. Theta invariant under Lorentz transformation. There are one more invariant tensor that we like to discuss, which is the Levi-Civita. I will keep an underline here because we will see that in general it is a pseudo tensor. We will define it later. So what is this? So this is a 0,4 rank tensor, or we'll see rather a pseudo tensor later on. They have these indices mu rho sigma. This is the component of it. It's completely anti-symmetric in these four indices. So if you specify one of the indices, then it will completely specify the value of this component or epsilon. So in our convention, we will choose the following: that 0, 1, 2, 3 is +1, and any cyclic permutation of these indices, sigma, will give you +1 under any cyclic permutation. Okay. For example, if you permute like that, they bring sigma here and so on. So sigma mu nu rho, same as the mu nu rho sigma, likely permutation. And if you do any other non-cyclic permutation, it will give 1. Suppose you interchange any to the index. So epsilon mu nu rho sigma is equal to minus of epsilon mu rho sigma. And it's a completely anti-symmetric. So if you set any of the two indices to same value, it will be 0. So for example, epsilon 0, 0, sigma is 0. Multiple index cannot take the same value. It's a completely anti-symmetric. Now it can be shown that only under proper Lorentz transformation, it is an invariant tensor. Here it is very important to note that only under proper Lorentz transformation. Remember, the proper Lorentz transformation is classified by the fact that determinant of is +1, and we leave it as an exercise for you to show that. We'll end here, and thank you for listening.